Greetings and welcome, friends. Mr. Wada here. We're going to talk about 3 more theorems regarding triangles and similarity. And this one's called the TPT, the Triangle Proportionality Theorem. And it turns out, how convenient, it also has a converse. It turns out that if one line is parallel to one side of a triangle, and it intersects the other two sides, then it divides the two sides proportionally. Hey, check this out. I just found this on the internet. It's got to be true. Here's like a GeoGebra demonstration or something that I can... Ooh, that's not actually helpful, I don't think. Not that one. But yeah, it turns out that, well, you see the ratios there, that even if I change this, that one side is going to result in those ratios being identical. Let's see, can I land that reasonably well? Oh, I'm zoomed in. There's my problem. 175%. What sort of screen space realty do you think you got here? Now, we've actually known that this was true regarding mid-segments, which would be when A and B were congruent to each other, but it turns out you'll have two similar triangles even when not. And this occurs anytime you have one side parallel to another. Oh, I think they highlighted the red dots to indicate those are the ones that I can manipulate. I can't change E. Yeah. Ah, that was I like that. I can't click and drag E, whereas they will let me click and drag D. Yeah, because E is defined based on D. So, triangle proportionality theorem, if you have a parallel line, it makes triangles that are proportional. Also, the converse is true. If a line divides two sides of a triangle proportionately, let's see, actually, did I label this right? RT is to TQ, yep. And also, these would be proportional to the entire length, by the way, but whatever. Then, what happens is that the lines will be parallel, or it will be parallel to the third side. Yeah, so the converse is also true. So let's put this to work, friends. Learning theorems and putting them to work. All right. In the diagram, QS is parallel to UT. RS is 4 as labeled. Bunch of things are labeled. What's the length of RQ? What could I do? Let's label it as X. Could someone set up a proportion for us? What could I do? What could I compare? Square roots. 4 over 6 is the same as x over 9. I like it. Yeah, divide by 2, I get 2/3. Let's multiply both sides by 9. Right, and once I set up the proportion, then it's just simple algebra. X is equal to 9 divided by 3 is 3. 3 times 2 is 6. All right? Proportionality. Excellent, excellent. All right. Oh, also, here's a random shoe rack. For example 2. Solving a real-life problem. Remember shoe racks? What if you had a shoe rack like this? I was actually thinking of designing a shoe rack that, like, descends into my basement from my front mudroom, and it would just be like on a little elevator. It'd be pretty cool because then I'd have a lot of space for shoes. Not that I own a lot of shoes, but I've got a lot of feet in my family, and so that'd be helpful. Well, don't spoil it on the internet. BA is equal to 33. Oh, I'm going to need a darker color here. So BA is 33. CB is 27. CD is 44, and DE is 25. Explain why the shelf is not parallel to the floor. The floor would be parallel to AE, which is resting on the floor. I could disprove parallelity by showing that these are not proportional to one another. So I'm going to show that 27 over 33, I'm asking, is that equal... Wait a minute, did it 44 over 25? No, not even close. What? No. That's like, this one's less than 1, this one's bigger than 1. I'm just going to say no. It's just no, I'm not even going to reduce that. No, not parallel. Why? By the converse of the triangle proportionality theorem. Bam. Believe it. I don't know. I was trying to find... I don't know if these acronyms are even helpful anymore. Are they? Yeah. Yeah. I don't know. I'll have to map that out, compare the theorems per day graph, and figure out what that rate is. Yeah, per unit. Yeah. Oscillation. Theorem 8.8, 3 parallel lines theorem. Check this out. If 3 parallel lines intersect 2 transversals, so notice L and M are not claimed to be parallel. L could even be off at like some crazy angle here. It turns out that it then divides the transversals proportionately. All right, so this over this is going to equal this over that. All right, that's kind of like the trapezoid mid-segment theorem. It's very similar. If you think about these two shapes are going to be trapezoidal in all instances when L is not parallel to M. And yeah, the trapezoidal mid-segment theorem divided it evenly, but it turns out that this divides it proportionally. So WX, I could slide it left or right. Those proportions would remain, well, those distances would obviously change. And then, yeah, if L and M are parallel, those would be parallelograms, and they would also still have those. All right, example 3, friends. Here we go. Ooh, this one's about streets in a town. Guys, we ride on streets. It's amazing. This problem so relates to me. What? Wait, we have a South Main Street, you're telling me? We have a 2nd Street? So anyways, check this. Angles 1, 2, and 3 are all congruent. All right, let's work with that fact first. By corresponding angles theorem, I'd be able to prove this parallel to that, and by corresponding angles theorem, I'd be able to prove this parallel to that. By transitive property, kind of, you'd be able to say the first and third are parallel to each other as well. This appears to have the 3 parallel lines theorem in play. So if this is 120 yards, and this is 150 yards, and this is 300 yards, I hope they're going to ask us for GH, but they didn't. They asked us for HF. So guys, 2 options. I could call this X and find this amount, and then find the total amount by adding those, okay? Or I could actually add these 2 together first and compare total length over little length and total length over little length. All right, so 2 options are here. I'll directly use the theorem though, Ryan. I know you're looking up another possible means, but we'll use this one first. X over 120 is equal to 150 over 300. That's a half, friends, right? That looks like a half if I ever saw one. Did you ever see that, a half? Yeah. That's a half. Yeah. Multiply both sides by 120. Half of 120, I get X equals 60. Yeah. Wait a minute. Oh. Aha, the 300. Yeah, it's 2 to 1. Guys, Waddy fail. Make sure this is added to the Waddy fail montage at the end of the year when you take the best Waddy fails and compilate them into a top 10 countdown list. All right, so this is, yeah, the reason I failed was I compared X to 150, and those are not in kind of corresponding positions there. It should have been X over 300. Although, oddly enough, even the disproportionality here didn't necessarily lead me to that conclusion that I was wrong right away, because sometimes we know that our drawings are so not to scale. Anyway, So this was actually 2 over 1, so that x is equal to 240. That's not even helpful anymore. 240, bam, done. So if this is 240, what's the length of HF? Yeah, I can add those together using one of our very first postulates we ever learned. Do you guys remember it? The big segment? Yeah, segment addition postulate. Oh, guys, it was so adorable when we were just baby geometricians. Remember that? Oh. Yeah. Yep. Actually, Finns, who developed the sauna, pronounce it sauna. Finns do. There are Finnish people in America. Sauna. Sauna. Sauna, yeah. I've grown up with saunas. Yeah. All right, guys, check this out. Angle bisector theorem. It turns out this over this is proportional to that over that. For an angle bisector in a triangle. Triangle. Okay. Here, let's see this in work a little bit. Maybe I can zoom in a tad here. So notice I've got the ratios of dA over they did dA over dC compared to that over that. Well, same difference. It'll still work. If I move this, notice those ratios maintain. That's constructed by an angle bisector, and it works. That's pretty cool. That's pretty cool. So that's the triangle angle bisector theorem. Yeah, that's pretty good. Let's do a quick example of that one. So many theorems and only about an example per theorem. That's okay. Here we go. Example 4. In the diagram, these angles are congruent. That means then, by definition of angle bisector, PR is an angle bisector. Oh, tricky sauce, guys. They done tricked ya. What could I do to solve for x? This is to this as that is to that. What is QR? (15 minus x). That's a use of our classic segment addition postulate and the subtraction property of equality. This QR plus x is equal to 15. Subtract x from both sides, you can find QR. Well done. So that means 15 minus x over, I'm going to put it over 7. You could put it over x. Doesn't matter. Over 7 is equal to x over 13 is the way I would have set it up. Let's solve by cross multiplying. Whoop, whoop. So I'll write this out very slowly so we don't forget to distribute, because that would be a common mistake. Oh, can you shut the door, please? Thanks. Thanks. I'm just so loud for my neighbors. Not like all the way. It actually blocks sound pretty good. I'm impressed. 13 times 15, 130. Nope, guys, I'm failing at that. I'm doing bad at 13 times 15 right now. 15 squared is 225. 225 minus 30 is 195. Yeah, that works. Minus 13x equals 7x. Add 13x to both sides. That's 20x. Huh. Well, that's okay. So let's see. So I'm going to get x is equal to 9.75 is what your book says. Yeah, normally they give us problems with super friendly whole number integer answers, but yeah, life isn't like that. And it is diversity day here, so decimals and fractions, they deserve some attention too. It's true. All right, well, thanks for watching, internet friends. Bye-bye.